Welcome back. Here we are beginning chapter 13. One more chapter after this to finish the course. So, chapter 13 is going to be covering solutions. And for us to understand what solutions are, these are the topics we're going to cover. We're going to first define what a solution is, what is the solute, and what is the solvent. Then we're going to see how the solubility of solids relates to temperature. We will also see how the solubility of gases relates to temperature. Then we're going to put everything into numbers by learning how to do mass percent calculations and using mass percent, which is going to be also another conversion factors to do problems with it. The same way we're going to use molarity, and molarity is moles over liters, and it's going to be another conversion factor, and we're going to use it to make calculations. And in particular, if we have an ionic compound, we're going to see how when we dissolve something, it breaks into the ions, so we can also calculate the concentration of the ions. Then we're going to see, and it's probably something that you have done a lot of times, we are going to see how we can dilute a concentrated solution, but we are going to learn a formula so it tells us exactly if you want this much concentration, you better take this much from the original solution and add water until you reach this volume. And that's one of the things that you're probably going to be using if you ever work on a lab or even on a kitchen or something like that. And once we do that, then we're going to see that most of the chemical reactions you can carry on the lab, most of them you're going to have solutions. So we need to find out how can we calculate the amount of moles on a given volume so we can do a stoichiometry with it. And then we get to do theoretical yield, percent yield, and all that kind of stuff with solutions now. You already know how to do it with gases using PV equals energy, and you definitely know how to do it with grams, changing the grams to moles. So every time we do a stoichiometry, we have to use moles. Grams to moles with molar mass, pressures, volumes, and temperatures to moles using PV equals nRT. And now we're going to learn how to do that with solutions using the molarity. And once we do that, we're going to learn something very similar to molarity, but it's going to be molality. And we are going to see how we can use that term to be able to determine, for example, how much salt do I need to put on the roads to prevent the roads from freezing when it starts snowing or something like that. And at the end, we're going to learn to connect chemistry to biology by understanding osmosis from the point of view of everything we are going to learn from solutions. So let's begin by understanding what solution, solute, and solvent are. And let's start with this. What is a solution? So you already know this. A solution is nothing more than a mixture, which means you're going to have at least two components. But if you remember from chapter 2, I believe, mixtures themselves can either be homogeneous or heterogeneous. And we learned that very early on the semester. So solutions are going to be only the homogeneous mixtures. So you can say, to summarize, you can say that a solution is the same as a homogeneous mixture. That's what a solution is, a homogeneous mixture. Classic example, you take water, you take table salt or sugar, you put it on water, and the sugar or the salt disappear, and you only see one thing. Remember, homogeneous, you only see one thing. Heterogeneous, you can see two things, like oil mixed with water. So that's what the solution is, nothing more than a homogeneous mixture. Given that this planet and your body, and mostly everything around you that is relevant, is mostly made out of water, our planet and our body are around 70% water, the solutions that we are going to see the most and the most practicals are going to be solutions made out of water, with water, and using Latin from aqua, which means water in Latin, we're going to say that an aqueous solution is a solution where you have water dissolving something. So now you know what a solution is. Now you know what an aqueous solution is. A solution where the solvent, or what you're using to dissolve, is water. And with that, you can probably determine this daily work. So we know that a solution is a mixture. A, B, C, D are solutions. We know they're mixtures. Are they solutions? So how does a solution form? Well, let me borrow something from this slide. Oops, sorry, that's not what I wanted to do. So let me take this for a second and bring it over here so we can work on it. So how does a solution form? Well, a solution is a mixture. So let's say that you have water on this beaker. So you got water in there. And that's only one component. And I want to take, for example, a salt shaker full of salt, and I want to put some in there. So this salt is nothing more than NaCl, right? And we know that NaCl is made out of Na plus and Cl negative. The sodium is on group 1 with 1 valence electron. Chlorine is on group 17 with 7 valence electrons. So the sodium loses 1 electron to be like an overgas, becoming positive. The chlorine gains an extra electron, becoming negative, and positive love negative. They come together and make a compound. So there's a force, and this is an intramolecular force of some kind, right? Because it's kind of keeping those together. However, ionic compounds are not just two atoms. It's a network of those atoms. So there's going to be a chloride over here, a sodium over there, a sodium over here, a chloride over there, and it even comes to the front, and it's going to make like a perfect cube. So, and I challenge you, if you can get a magnifier, go grab a grain of salt and look with the magnifier, and you're going to see perfect 90 degrees angles, a perfect cube. So this perfect cube is made out of those ions. So you have those ions going around everywhere. And you're going to put that salt into the water. And what we're going to find out is that the moment you put it on the water, and what do we know about water? We know that water have a Lewis structure like this. And we also know that water is going to be a polar molecule. So we learned that recently. So water is going to be like that. So what happens here? Once more, the same way this positive is attracted, this negative is attracted by this positive is attracted by the partially negative from the water. So you begin feeling an attraction there, and this would be a ion dipole attraction. because the Na plus is an ion and the polar molecule is a dipole, partially negative, partially positive, right? And while that is happening, there's another water molecule over here. And this one have the partially positive closer to the partially negative, and there's a force in there. So the water is pulling this sodium this way. The water is also pulling the chloride this way. And there's not just one or two waters. There's going to be as many waters as can come close to this chloride negative and sodium positive. And between all of them, the force, so there's going to be water everywhere pulling on those. Between all of them, these forces pulling that way and these forces pulling that way, all these forces combine. So all these forces are going to be acting there, combined, grabbing that sodium, and all this water, as many as we can put there, pulling on that. That force is going to be more than the force that was holding them together. When that happens, when a lot of water molecules have a force that is stronger than the force between the ions will come apart and they will separate. So the perfect cube that I told you before is going to separate like that. But remember, I told you that the water was pulling that. So water, I'm just going to do something like this for what that equals water. The water is going to be around each one of those ions. And they're actually maintaining those ions prisoners inside a cage. And the scientific way of calling this, we call this hydration, because it's water, hydration cages. When water surrounds each ion and keeps them separate from each other, therefore, they have been dissolved in water. So if by any chance, if I start boiling that solution, the water will start evaporating and the ions will come back together. And that's what you see if you do that on your stove. Water evaporates and you come back with and you end up back with the salt. But as long as there's water, those ions are going to be inside those hydration cages, and that's what we call a solution. So let's put some names into this. If you notice, and let me show you here, for every, remember this is representing water, for every ion, you're going to need a lot of waters to keep them separate. So a lot of waters for every ion that you trap in there. So this tells us that the substance that you're using to dissolve something, in this case the water, is the one on the bigger amount, because you're going to need a lot of them for each one of them. Bigger amount, on this case, is the water. The smaller amount, on this case, is going to be the NaCl. So when you have a solution, one of the components is going to be on the bigger amount, the other one is going to be on the smaller amount. The one that is always on the bigger amount, we call that the solvent. The one that is on the smaller amount, or the one that you are dissolving, we call that the solute. So the solute is what you are dissolving. The solvent is what you're using to dissolve it. Both of them combined is what we call the solution. So the solution is the combination of the solvent and the solute, and you know that the solvent has to be in the bigger amount because it's going to have to form those hydration gauges, which requires a lot of those solvent molecules to trap the ions. Therefore, they have to be on the bigger amount. So now you know what the solvent is, now you know what the solute is, and you know that the combination of both is what we call the solution. So with that said, you should be able to answer this question. And once you do that, we have to understand something else. So before we even look at the question, if these are mixtures, this will be my homogeneous, because I can only see one thing, and this will be my heterogeneous, because I can see component 1 and component 2. The color at the bottom is just a reflection. On this one, I can only see, I know there's 2 components, but I can only see 1 component. I only see the clear liquid. So just a quick refresher from what we did at the beginning of the semester. So the question is, what does like dissolve like means? Like dissolve like. What does that mean? What that means is what we just saw here. We saw that the NaCl, which was plus and negative, had to be dissolved with a polar molecule. So because these have charges and there's a separation there, this will be polar and the water is polar. Can I dissolve sugar in water? Yes, sugar contains a lot of OH groups, which are polar groups. So sugar is polar, water is polar. So yes, I can dissolve it. So what's happening here is we got water, which is polar, and oil, which is nonpolar, and they do not dissolve, because for them to dissolve, they have to be like or similar, like, dissolve, like. Polar, dissolve, polar, and non-polar, dissolve, non-polar. And you already know, if I give you the formula of a compound, you can do the Lewis structure, you can do the shape, you can do the electronegativity analysis, and you can tell me if the molecule is polar or not. So with that said, you should be able to answer this problem. And once you do that, then let's learn some other terms. So what terms are we learning now? Saturated, unsaturated, and supersaturated. For that, let me do a drawing here. So let's say that this is going to represent water now. So I'm going to put water, 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 water. So all this is full of water. Okay, so water is everywhere, right? And now let's say that I'm gonna put, let's take a good one here. That would be, let's use this one. And this one is gonna represent sugar. So if I put sugar in the water, which is going to be a solid, so it's gonna be a bunch of them together. So the same thing that happens with the salt before, where I told you we can put the water around and the water start pulling that way until this comes apart. So as we break those apart, let's say that you're gonna need 4 waters for every 1 sugar. So I'm assuming that the hydration cage is gonna require 4 waters for that, right? So when I start dissolving that, 1 sugar goes there, another sugar goes there, another sugar goes there, that continues on the back, another sugar goes there, another sugar goes there, another sugar goes there, and there, one there, one here, one there, and put there, there, and there. And what I'm trying to show is that at this point, every single molecule of water is busy surrounding or encaging that molecule of sugar. When every single molecule of water is busy, we said that this is a saturated solution because every single molecule of water is being used to encase the sugar in this case. So what would be an unsaturated solution? An unsaturated solution would be one that still have water available. So if I put more sugar in there, water will dissolve it because they're still free. They are not busy yet. So the unsaturated, you still have water available or the solvent to encase the ions or whatever you bring in. The saturated, every single molecule of the solvent is busy. And the supersaturated is a special condition. On the supersaturated, I probably got the water really hot first. And because of that, and this is an analogy, because of that, once every water molecules became busy, somehow, because I increased the temperature and so on, somehow I was able to squeeze one more molecule of sugar in between every somewhere. So the water is basically working overtime now. It doesn't only have to encase one ion. Now the same amount of water is gonna, because it's really hot and it's moving faster and can separate better, now it's encasing more. So it's going over the capacity because I'm forcing it to. That would be a supersaturated solution. One really interesting thing about supersaturated solutions, there's a lot of stress in there. So I can have a solution that is totally clear, very homogeneous, and I can just tap on the glass, and I can see the solid forming really fast in front of my face. It's really spectacular to see a supersaturated solution that get disturbed, and the solid just jumps out of the solution. But the ones that you're used to see, are the unsaturated solution, because once you see a saturated solution, if I put something more on it, it's not going to dissolve, and it's basically going to go to the bottom. For example, if I have a glass of water and I take a solid, let's say, for example, potassium nitrate, and I put a lot of it in there, as long as I have water still available, it's going to dissolve. The moment every single molecule of water is totally busy, the next piece of solid that I put is just gonna go and do this. It's just gonna go to the bottom. And it's gonna stay there because it cannot be dissolved. Every single water molecule is busy. So when you have a saturated solution, you cannot dissolve anymore. Whatever you put in there is gonna go to the bottom. So with that knowledge in mind, you should be able to answer this challenging question. And it's not challenge. You just have to apply what you just learned. And I would like to see you taking each one of these flasks and say, well, my liquid is gonna be up to whatever you think the liquid is gonna be, and will there be anything at the bottom or not, or what? How will I draw that? So try to visualize what's happening and try to represent it on a drawing. Notice that the flask is a 2,000 milliliters or 2-liter flask, and you're using only 1 liter of solvent and so much of the solute. So what will happen based on this information? Okay? And once you do that, then we will have covered, and hopefully you have a very good grasp of the concept of on what a solution is, which part of the solution is the solute, and which part of the solution is the solvent. And in the process, we also learn about saturated, unsaturated, and supersaturated solutions. So with that, I leave you there so you can practice some more before we move into the next topic, which is going to be the solubility of solids. So I told you how a solid dissolves. So how can we relate that to the temperature? So that's what we are going to discuss once we come back. So see you soon. Take care.